A decentralized trust framework for emergency communication using DTN. Abstract: this paper addresses mitigation of malicious behavior in mobile and vehicular sensor networks under a mobility-aware scenario characterized by frequent disruptions. Delay-tolerant networks, DTNs, are network architectures that have been developed to cope with intermittent connectivity in sensor networks. DTNs use an end-to-end message-oriented overlay called the bundle layer, which is above the transport layer, to help combat network interruption. In DTNs, malicious behavior poses serious threats in forwarding messages from the source to the destination node. In this paper, we propose a mobility-aware trust management scheme which utilizes subjective logic to dynamically filter out misbehaving nodes in DTNs. We develop trust relationships from encounter record histories that have been exchanged by nodes to evaluate trustworthiness. We perform a comparative analysis of our proposed scheme with different mobility models against encounter-based routing, EBR, which is a trust-based routing scheme, and non-trust-based, profit and spray and wait, routing schemes. The results demonstrate that our scheme can deal with routing misbehavior such as packet dropping attacks and outperforms EBR and the non-trust-based routing schemes without incurring high message overhead. Introduction. Delay/disruption tolerant networks, DTNs, are networks developed to cope with intermittent connectivity and long delay in wireless networks. Unlike traditional networks where packets are forwarded along fixed links, DTNs use a store-and-forward approach to overcome the lack of end-to-end paths. 1. DTNs comprise of nodes with limited resources such as buffer space and power. These resource constraints, in addition to the sparsity and mobility of these nodes, often result in intermittent connectivity. The application of DTNs spans across a wide range of applications including underwater networks, UWNs, pocket-switched networks, PSNs, vehicular ad hoc networks, military applications, and disaster recovery and rescue operations. 2. 3. Mitigating routing misbehavior using reputation and trust management schemes has been well studied in wireless networks too. However, there is no adequate attention to trust and reputation systems in DTNs. Although trust management and reputation-based strategies have been well studied in mainnets, the unique network characteristics of DTNs such as lack of end-to-end paths, unpredictable mobility patterns and long variable delays make these schemes unsuitable for DTNs. 4. Recent works in DTNs based on trust management show the challenges in message forwarding where routing misbehavior from malicious nodes reduce the message delivery probability. 4.9. For instance, DTN evaluates the trustworthiness of a recommended node by using its encounter value. This trust recommendation may come from misbehaving nodes that collude with each other to degrade the network performance. Proposed trust management schemes are not adequately effective to filter out dishonest recommendations. Another proposed scheme 4 relies on a trusted authority, TA, to evaluate nodes' behavior, which is costly in terms of transmission overhead and verification feedback. Additional security requirements will translate to more energy consumption, which is a major challenge in DTNs. In mission-aware applications deployed using DTNs such as disaster recovery and rescue operations and tactical military warfare operations, DTNs must achieve their mission despite disruption or compromise of nodes. To deal with these limitations, we propose a mobility-aware trust management scheme, MATMS, for DTNs. We focus on mobility-aware models that capture some degree of recurrence in modeled activities such as the post-disaster model, PDM. 3. Nodes maintain a set of neighbors that they encounter recurrently. We develop a trust relationship from the inter-contact graph formed from the encounter records. Compared to the approaches in 4.9 which rely on direct and indirect encounters to formulate trust, we develop a novel approach using subjective logic. Consensus and discounting approaches from subjective logic are used to formulate trust networks. The consensus approach deals with self-promoting attacks while the discounting approach deals with colluding attacks. The main goal of our approach is to increase delivery ratio and reduce message delay in mobility-aware DTNs. We combine opinion splitting from trust network and latency distributions from the inter-contact graph to provide QoS in making forwarding decisions. The MATMS simplifies trust graph into series parallel graph by the removal of uncertain paths to obtain a canonical graph. Trust transitivity means that if node I trust node J which trust K, then node I will trust K, which is achievable through indirect trust from node K to I as illustrated in Fig.1. Trust is a dynamic property in DTNs as a result of the changing network topology. In our proposed scheme, trust is aggregated along with uncertainty, which makes the aggregated value more reliable than other approaches. Trust is incorporated into the routing decision to protect against packet malicious misbehavior such as dropping attacks. We use subjective logic 11, which is suitable for the analysis of networks as trust relationships can be expressed as opinions with degree of uncertainties. To establish trust using subjective logic, we express binomial opinions as trust and map them into probability density function, PDF. A belief system is developed to evaluate the trustworthiness of a forwarding node based on the inter-contact graphs. This belief, which is expressed as opinions, will not only reflect a node's trustworthiness towards another node but will also reflect the confusion because equations do not balance dimensionally. If you must use mixed units, clearly state the units for each quantity that you use in an equation. Belief of the prediction through the measured uncertainty. The trust opinion formed from these nodes as they come in contact with each other are used to make forwarding decisions. To validate our proposed scheme, we implement extensive simulations in 112 Simulator to reflect mission-critical scenarios using the Post-Disaster Model, PDM, 3, RFC 7576-13, which is a reference model for emergency support and disaster recovery, and compare the performance of our proposed scheme with existing benchmark schemes when nodes are compromised. Simulation results show that MATMS mitigates routing misbehavior without incurring high message cost under best trust formation. The rest of the paper is organized as follows. We discuss related work in Section 2. The network scenario, attack model, and design goals are presented in 3. In Section 4, we introduce some background work on subjective logic and present our proposed scheme. We carry out a performance evaluation in Section V to evaluate the performance of our proposed scheme and conclude our work in Section 6. 2.2. Related work. In this section, we discuss the existing trust and reputation management schemes in peer-to-peer, P2P, and WSNs, mobile ad hoc, and trust management schemes in DTNs. A trust management in P2P and WSNs. In the context of P2P networks, trust management schemes are distributed. There is no central authority to monitor and evaluate the trustworthiness of nodes in the network. Each node monitors and evaluates the trustworthiness of its neighboring nodes. In structured P2P networks, a decentralized trust management scheme which uses a P2P lookup system based on a search tree that is virtually distributed is proposed by 14. Each peer is assumed to be a trustworthy neighbor unless a complaint is received by the virtually distributed tree search. The authors in 15 propose eigentrust, a secure and distributed strategy to compute global trust values based on iteration. This global trust is computed using transitivity and stored in a content-addressable network, CAN. Similar to the approach in 15, a decentralized reputation-based trust-supporting framework, peer trust, with an adaptive trust model for evaluating the trustworthiness of peers based on a transactional feedback system is proposed by 16. Both eigentrust and peer trust use the trustworthiness of the recommender to evaluate the indirect trust. The authors in 17 propose a new fair scheduling technique, power trust, to leverage the power law feedback characteristics. This robust and scalable P2P reputation system uses a distributed ranking mechanism to dynamically select nodes that are most reputable in a P2P network. In unstructured P2P, the trust queries are generally flooded to the network. A detailed model for trust computation is not defined in the model as presented in 1821. Peers use collective feedback in decision-making to mitigate inauthentic file downloads, including packet drop rate, control packets, and data packets. Each node stores these weighing mechanism in a trust table and sends feedback to the selected cluster heads. In event-driven WSNs, authors in 25 propose a reputation-based protocol, TIBFIT, to diagnose and mask arbitrary node failures. This protocol analyzes the binary reports from neighbors to determine the occurrence of an event. An active detection-based security, active trust, and trust scheme is proposed for WSNs by 26. This trust-based routing scheme uses the trust level of neighboring nodes and the trust requirements of a packet to select an optimal forwarding path. Active trust creates detection routes to compute nodal trust, thereby preventing black hole attacks and optimizing the lifetime of the network. An integrated trust management framework, ITrust, is proposed in 27 to evaluate the trustworthiness of nodes in the neighborhood using monitor nodes. These special nodes gather information about neighboring nodes and share their trust indices with encountered nodes, which is used to make forwarding decisions. BB Trust Management in Ad Hoc Networks. In ad hoc networks, several schemes have been proposed and discussed in a comprehensive survey by 28. A recommendation-based trust model with a defense scheme has been proposed to filter trust propagation attacks using clustering techniques 29. This scheme pays attention to attacks that are related to dishonest recommended from neighboring nodes in a particular time frame based on the number of encounters. To measure and model trust evolution, an information theoretic framework is proposed in 30 using entropy and probability to acquire, maintain, and update trust behavior that are associated with the behavior of nodes. In the proposed framework, propositions are developed to establish trust through third parties, assist in route selection and malicious node detection. In 31, authors extend the notion of traditional trust to data-centric framework for the establishment of trust based on several evidence techniques. They pay attention to network systems that are highly volatile and resource-constrained and use the theory of Dempster-Schafer to evaluate data reports and compare their results to weighted and Bayesian schemes. In 32, a fully distributed public key certificate management based on trust graph and cryptographic threshold is proposed. In this model, users can issue public key certificates and also perform authentication using the certificates. The threshold cryptography is used to check misbehaving nodes that issue false public key certificates. See Trust Management in DTNs. To maximize delivery ratio and reduce the transmission cost of messages, an encounter-based routing, EBR, 10 has been proposed to evaluate the trustworthiness of a node when it encounters another node. This routing strategy uses an encounter value, EV, which is a reputation metric obtained from a current window counter-forwarding evidences. EBR has been widely adopted for DTN routing as most research works in DTNs leverage on its routing strategy. In 6, a novel methodology is proposed to deal with malicious and selfish behavior. This trust management protocol, which incorporates QoS, is based on stochastic Petri net, SPN, and is designed to optimize the routing performance in DTNs. Extensive simulation analysis has shown that the proposed scheme outperforms Bayesian trust routing schemes, epidermic and profit routing protocols with a lower message overhead. Similarly, authors in 33 propose a provenance-based trust model, PROVEST, for accurate peer-to-peer assessments. In this model, a data-driven strategy is used to reduce the consumption of constrained resources. The authors in 5 propose a graph-based iterative algorithm as a robust trust mechanism for node detection. In a comparative analysis using extensive simulations, authors have illustrated that their proposed scheme performs better than other trust management schemes such as the Eigentrust and Bayesian framework 15 under Byzantine attacks. A probabilistic misbehavior detection scheme, PMDS, has been proposed by 4 based on data forwarding evidences. In this scheme, the inspection game in 34 is adopted to demonstrate the cost of misbehavior detection. Simulation results show that there is a reduction in the forwarding cost that is incurred by ITrust and that ITrust effectively detects routing misbehavior by the malicious nodes in both single and multi-copy routing protocols in DTNs. To reduce the detection time and improve precision, a collaborative contact-based watchdog, COCOWA, which is based on a local watchdog detection, is proposed in 35. When a node encounters another node, a diffusion module is used to transmit and process false positives and negatives. Analytical and experimental results presented using the proposed scheme show that the detection time and reduced as well the message transmission cost when nodes collaborate using the diffusion module. Encounter with node, it may assume the encountered node is malicious. In ad hoc networks, trust degrades automatically as the number of hop increases. This may not be true in DTNs as node rely on a hop-by-hop forwarding approach. Filtering out malicious nodes that propagate false recommendations has not been effectively tackled in Monets. These nodes collude with each other and exaggerate trust rating across the network. In DTNs, trust management schemes proposed focus on selfish behavior. Most schemes use mobility models such as random waypoint, RWP, which is inadequate to model trust relationship from transitivity. Game theoretic models such as ITrust effectively detects misbehaving nodes but vary network scenario, attack model, and design goals. DA network scenario. We consider DTNs deployed in mission-aware scenario. We adopt the post-disaster model, PDM, proposed by 3 and recommended by IETF, RFC 7476, as a baseline scenario for disaster recovery operations 36. We assume that the disaster scenario consists of a group of nodes deployed in an open and hostile environment such as the Great East Earthquake in Japan, 2011, where over 375 base stations were destroyed, over 90 routes were disconnected from the relay transmission lines and the traditional telecommunication services were unavailable 37. In this scenario, we consider a community of interest where there is a DTN with several wireless devices, I.E nodes, moving in a community which are either held by people or fixed on vehicles, data mules. This scenario is based on the PDM in 1 shown in Fig 2. Nodes move from one subtask to another as needs arise during mission executions. A node can also move around multiple subtask groups if it is assigned to multiple subtask events described in the movement models, such as between center movements, which is the movement between the coordination centers, which include the relief camps, evacuation centers, medical centers, and the police and fire stations. Other mobility patterns undertaken by these responder nodes include event-driven, cyclic route, and convergence move. To protect a network from a wide range of attacks, Traditional security mechanisms are not robust enough, especially with networks that lack end-to-end connectivity and a predefined network architecture. In DTNs, malicious nodes aim to break routing capabilities in addition to dropping packets and exhibiting selfish behaviors. A malicious node can be an internal attacker with the aim of disrupting the operation of a mission, such as disaster recovery operations and in tactical warfare scenarios. When two nodes meet, an encounter record is generated. Assuming node I comes in contact with node J, an encounter record area is generated as shown below. Definition 1. An interaction area between two nodes can be expressed as follows. Where NI, New Jersey, and DST are node identifiers for node I, J and the destination node. FLI and RLI represent the list of messages forwarded and received by node ITS as the timestamp, while TMEXP is the expiration time of the message. Due to the resource constraints, a node keeps its most recent ER to reduce computational overhead. B. Attack model. In mission-critical or situation-specific scenarios like tactical and post-disaster communication networks using DTNs, malicious nodes can launch an attack by dropping packets forwarded to them. An attacker first receives a packet relayed to it, then it drops them with a certain probability, which can lead to serious performance degradation. Malicious nodes can drop packets forwarded to them even if they have enough buffer space to store these messages. 1. Self-promoting. Malicious nodes manipulate their own trustworthiness. This can be done by falsely increasing their probability of expectation. The main purpose of this attack is to attract packets and drop them later. 2. Time-dependent attacks. Honest nodes can start misbehaving after a time interval. This malicious behavior can provide false recommendations at different time intervals, which will lead to the malfunctioning of the whole trust management framework. 3. Bad-mouthing attacks. Providing bad recommendations to tarnish the reputation of well-behaved nodes may lead to a decrease in their chances of relaying packets across the network. Such fraudulent behavior prevents nodes from relaying packets using the best routes in the networks. Trusted nodes can conspire to propagate these unfavorable rating of healthy nodes. 4. Ballot stuffing attacks. This attack aims at misleading the trust management framework. Providing compromised nodes with good reputation based will result in over-exaggeration of the reputation of nodes. This attack increases the chances of relaying packets through malicious nodes so that they can drop or tamper with packets relayed to them. 3. Proposed framework. The trust computation is based on the history of encounters known as the encounter record, ER. Suppose two nodes I and J come in contact with each other. ER generated by node I about node J is denoted by ER equals ER1, ER2, ERN, where ER1 is a single interaction record with node J. We describe how trust can be derived with the belief of subjective logic, which uses opinion as a belief metric. We briefly describe the process of deriving trust from nodes' interaction to form ERS. The stored ERS are used to form the trust relationship. This relationship is later converted into trust opinions. To quantify the trust value associated with the encountered node, the trust paths from the trust network is evaluated. Subjective logic operators, are applied to the trust paths to obtain a quantifiable trust value E. The latency distribution of the transitive paths is evaluated and the path with least average delay is selected as next message hop. A. Subjective logic. Subjective logic 11 can be described as a belief calculus which allows nodes to express their opinions about propositions as degrees of belief, disbelief, and uncertainty. Subjective logic is suitable for the analysis of trust networks, as trust relationships can be expressed as opinions with degrees of uncertainties to monitor the behavior of encountered and neighboring nodes in the community of interest. To establish trust using subjective logic, we express binomial opinions as trust equals B, D, U, where B, D, U represent belief, disbelief, and uncertainty. With accumulated forwarding evidences from encounter records, malicious nodes may provide compromised computed trust values. These trust values do not reflect the node's behavior if each record is treated equally regardless of time of encounter. In subjective logic, the notion of opinion can be expressed as a belief built on trust. We adopt 11, which uses trust transitivity to compute trust along a chain of trust edges. For example, two nodes I and J where I's opinion towards J is denoted by .ij, which is the trustworthiness of J towards I, can be described as on opinion vector. Definition 2. An opinion is denoted by an ordered triplet B, D, U, such that B plus D plus U equals 1, where B, D, U, 0, 1, and B, D, U represent belief, disbelief, and uncertainty. Definition 3. Consensus opinion, let I, J and K be 3 DTN nodes. then .ik equals bic, dic, duc, and .jk equals bjk, djk, IJERT b opinions respectively held by node I and j about the trustworthiness of node k. The consensus trust can be defined as .ik equals .ik. .jk, which is the combined opinion between .ik and .jk. The symbol is used to designate the consensus operator. .ik equals bijk, dijk, duijk, 1. The consensus opinion, which is equivalent to Bayesian updating in statistics, reflects conflicting opinions in an equal and fair strategy. Nodes I and j have opinions about the trustworthiness of an encountered node k from distinctive about node k. Combined opinions help in the reduction of uncertainty. The consensus opinion is an aggregated opinion from node I, j and k. Definition 4. Opinion discounting. Let .ij equals bij, dij, uj represent the opinion of node I towards j, and .ij equals bkj, dkj, ukj represent node j's opinion towards k. Node I will take the recommendation of node j toward k as. Opinion discounting, which is denoted by a discounting operator, is used to compute trust along a transitive path. 11. It shows how node I computes the indirect trust given by the knowledge of node j about k. Opinion discounting is derived from the discounting function by 38 using a discounting rate. Node I's belief in the opinion of j becomes the uncertainty towards node k rather than its disbelief, and node I's uncertainty in j also becomes part of the uncertainty in node k. Definition 5. The probability expectation value of a binomial opinion TIJ is expressed as E.ij equals bij plus auj, 2. Where bij, uj, a represent the belief, uncertainty, and base rate as described in 11. The expression in EQ2 is equivalent to the pygnistic probability 39 in decision theory. In 39, belief can be used to make decisions, and these decisions are quantified by probability functions. In the context of trust computation, .ij can be expressed as a trust opinion of node I on j. The value of .ij given in EQ2 represents the predicted value of the trust opinion .ij as a quantifiable value. A-B conversion of trust relationship. In general terms, a set of previous encounters is used to formulate the trust between two nodes. We describe this trust relationship with the following definition. Definition 6. The trust relationship Tg between two nodes is given as, where Tg denotes node I's trust in relation to node j, ERN is the total number of interactions between nodes I and j, A is the base rate, which is the prior probability in the absence of belief and disbelief, S, F represents positive and negative events from previous encounters, and the ERW represents the window size of the ERS. To convert trust relationship Tg into an opinion .ij, the probability density is expressed over binary events as a beta probability density function, PDF. Beta distribution is a family of continuous probabilities denoted by A, SS, on the interval 0,1. Let S, F represent the number of positive and negative observations from the interactions between nodes I and j. The beta, PDF, can be expressed as A equals S plus 2A and SS equals F plus 2, 1, A, 4. Where S and F represent positive and negative observations and A is the base rate. Adopting the approach in 11, we bijectively map between the opinion parameters and beta, PDF. See formulation of trust relationship with trust transitive paths. In DTN, a trust network can be conceptualized as a directed graph from the aggregation of individual trust relationships. The analysis of trust propagation is based on the notion of transitivity. Trust transitivity means that if node I trusts node j which trusts node L, then node I will also trust node L. There is a possibility of getting two or more cyclic paths. We consider a minimal path solution so that the number of transitive hops in the trust network is minimized. To represent trust transitive networks as directed graphs, we add some elements of notation to enable us express trust networks in a structured way as shown in EQ.8. We introduce an edge-splitting approach so that each node is connected to an independent edge, and TNI, L is expressed as D. Trust evaluation. The final stage of establishing trust between nodes is to compute the trust value of each node based on the trust relationship established from definition 3 and 4, which are applied to the edges that link the transitive path between the source and destination nodes. The trust relationship is expressed as a quantifiable trust value, which is the probability of expectation E, defined in EQ3. In summary, a node's trust inference system is developed by collecting and aggregating forwarding evidences from previous encounters, then it builds and stores the trust relationship and develops an assessment procedure for evaluating the trust value. A node's trust level is defined as a real number in the range of 0, 1. E-message forwarding scheme description. The primary goal of every DTN message forwarding protocol is to obtain a high message delivery ratio and good latency performance. Widely adopted message forwarding schemes such as MaxProp and Rapid achieve high delivery ratios with excessive consumption of limited network resources, while quota-based protocols such as Spray and Wait, Spray and Focus that have low message overhead are not able to achieve comparable message delivery ratios too. In traditional wireless networks, latency depends on the condition of the egress links. Packets remain in the buffer till the link becomes available. Latency in DTNs is quite different because the latency of a packet depends not only on the next hop but previously encountered node. We use the intercontact graph between two edges to calculate the latency between two encounters. We use the notation M1, M2 to denote a directed edge between two nodes that come in contact. Each edge is maintained by a finite order list of elements, two tuples, IJERT, which is the average latency elapsed from node I from an encounter with node J and K. We use edge splitting to produce independent paths to calculate the path latency as shown in Fig 4. We compute the path latency as IJL equals M1, L equals M2 so that the entry for destination node L has corresponding path latency of IJL and L as a parametric summary of latency distribution for node I to make its forwarding decisions. It is important for a source node to have an idea of the latency distributions to enable it make realistic estimations of the probability of successful deliveries to the destination nodes. 1. Routing decision. In mission-aware scenarios where the movement models have similar or recurring traffic patterns such as the movement between emergency centers in a disaster network captured in the PDM Model 3 and ETSI reference model for emergency recovery and disaster relief operations 36. It is important to achieve an effective forwarding strategy so that relayed messages use the optimal routing path to make forwarding decisions. In our proposed scheme, we do not only consider the trustworthiness of a node before making a forwarding decision. We pay attention to latency distributions formed from the interconnect graph from source node to the destination node. The proposed scheme concurrently considers the latency of each independent path and the trust metric from the probability of expectation in EQ3. Assuming node I encounters nodes J and K, node I can choose between nodes J or K as the next hop to relay its message to L based on the following steps. Node I exchanges its ER table with node J and K. There is a feedback mechanism for acknowledgement for each encounter. To evaluate the trustworthiness of an encountered node, the two nodes exchange their trust table and update their ERS. After the trust updates, node I will determine whether to forward the packets to nodes J or K based on the trust value and latency distribution from IL. This is a quality of service (QoS) measurement which enables messages to be forwarded using the optimal route. However, the trust values take precedence over the latency distributions. 2. ER aging in MATMs. To provide resiliency, we use an ER window ERW to check for collaborative attacks. A malicious node can exhibit a certain behavior such as starting up as a trustworthy node but later becomes a malicious node. This behavior makes the forwarding evidences collected before the node's change of nature misleading. To alleviate this problem, we create a window size where old assessments are discarded in a process known as ER aging. For every encounter, there is a TDS which is used in the assessment of the ERS for a particular ERW. Assuming node J starts misbehaving at time t25, mins, and the periodic rate of the ERW is t600, mins. If the prior forwarding evidences from node J is large, it will take a long time for its neighboring nodes to find out about the change in its behavior. For performance evaluation. AA simulation setup. This simulation is implemented in one simulator for DTN protocol evaluation 12. We simulate MATMs on top of the PDM model, random waypoint and shortest path map based mobility model. The PDM model was developed by 3 and recommended by IETF 36 for information-centric networks, baseline scenarios for emergency support and disaster recovery operations. The map-based mobility model constrains the movement of nodes the paths defined in the map data. The arbitrary map data defined in well-known text, WKT, is understood by the movement models in the PDM which are created using OpenJump, a geographic information system, GIS, program for converting real-world map data. We use 5 neighborhoods, 4 main centers, 10 relief and evacuation camps, 100 rescue workers, 10 supply vehicles, 10 emergency vehicles, 10 police patrols for the PDM simulation setup which runs for 48 hours. We use a simulation area of 4,500 × 3,400 m, at speeds of 0.5 to 1.5 km per hour for pedestrians and 2.7 to 13.9 km per hour for vehicles. For each of these scenarios, Data traffic is generated as a Poisson's process at the rate of 1 message per 5 minutes for a randomly selected source-destination pair similar to message generation adopted by 3. Similar to the approaches in 6.40, each node has a buffer size of 50 MB and the message size is in the range of 50 KB 5 MB. For each experiment, the simulation runs for 10 times with random seeds and the average of the metrics measured are presented. We use the same simulation setting to evaluate the performance of MATMs for shortest path map-based movement and random waypoint, RWP, mobility models. Shortest path map-based movement model. This mobility model constrains the movement of nodes to predefined paths. Different paths can be defined for a specific group or all the nodes in the network. Random waypoint, RWP. RWP is a synthetic movement model. It is a movement model where nodes randomly select their speed and destinations. In RWP, it is difficult to model a realistic statistical distribution of events. This is because RWP is an abstract movement model and does not capture realistic mobility patterns. We also conduct a comparative analysis comparing our proposed scheme to encounter-based routing, EBR, scheme. EBR uses an encounter-based metric which maximizes message delivery ratio while minimizing overhead both in terms of extra traffic injected into the network and control overhead 10. In addition to the EBR protocol, we evaluate MATMs against 2 other routing protocols, Profit 41 and Binary Spray and Wait 42. Profit uses history of encounters and transitivity to compute the probability of message delivery by a node while Spray and Wait sprays a limited number of copies, L equals 6, into the network, and then waits till one of these nodes meets the destination node. BB performance of MATMs. In this section, we consider the efficiency metrics and general performance that apply to many routing protocols. We focus on 3 performance metrics in DTNs, message delivery ratio, message latency, and message overhead. These metrics used in evaluation are described as follows. Delivery ratio, this is the percentage of messages delivered to the total number of messages created. Latency, the latency is computed as the average period of time that a message needs to travel from the source node to the destination node. Overhead ratio, this is the ratio of the total number of messages relayed to the total number of messages delivered. In Fig 4, A, delivery ratio, B, overhead ratio and C, latency, we explore the performance of MATMs with different traffic patterns in the PDM. In an emergency response network, the performance varies based on movement patterns. We evaluate the impact of malicious responders on these traffic patterns, rescuers to rescuers, RR, messages relayed by responders among themselves for the disaster recovery operation, patrol, police patrol and fire trucks, center to center, CC, between center movements. Similar traffic patterns are also captured in the ETSI reference model for disaster recovery and rescue operations 43 such as movement between casualty collection point, CCP, and temporary care center, TCC. In Fig 4, we show that under our best trust formation with percentage of malicious nodes varying from 0 to 50%, the delivery ratio remains high even with 50% of malicious responder. The latency and overhead also decrease as the number of malicious nodes increase because only trusted responder nodes take part in message forwarding, hence the path cost and delay have reduced and these metrics are calculated from source to destination nodes. CC comparison with other schemes proposed. In Fig 6, we present the performance evaluation results of MATMs alongside other routing protocols on the post-disaster mobility mode, PDM. It is observed that the map-based mobility model enhances delivery ratio for all routing schemes. This is as a result of the mobility pattern which yields more encounter opportunities, role-based, and event-driven models. Patterns in the PDM capture distinct movement patterns, hence they can achieve higher delivery ratio. Our simulation results in Fig 5 shows the impacts of malicious nodes on the network in different mobility model. We observe that our proposed scheme, MATMs, and the EBR scheme have less performance degradation in delivery ratio when compared Profit and Spray and Wait. This is because messages are forwarded to relay nodes based on trust and relay nodes must be trustworthy before a message is relayed to them. Our scheme outperforms EBR and the other routing schemes when considering message delivery. In Fig 5b, we analyze the impacts of the malicious nodes on message overhead for the different movement models. We observe that our trust-based scheme is significantly lower than EBR and the other routing schemes even with malicious nodes. Again, we analyze the impacts of malicious nodes on the message delay in the post-disaster model in Fig 5c. We observe that when the percentage of malicious nodes increase, the latency decreases because messages are forwarded to only trusted nodes and dropped messages are not considered in calculating the message latency. We can see that our scheme, which incorporates a node's latency distribution to make forwarding decisions, outperforms the other routing schemes. Mitigation efficiency with aging ER. In resource-constrained networks, nodes may have limitations in their storage capabilities which may affect the No of records kept by a node for an ERW. We evaluate the performance of MATMs and EBR with different ERW sizes. We consider collaborative attacks with a dropping probability of 0.6 under the same simulation setting described in section VA. In Fig 6, A and B, we show the false positive and the detection accuracy over a varying ERW. Our results show that a larger ERW size achieves a higher detection accuracy while reducing the false positive rate. The results also show that the detection performance of MATMs under varying ERW sizes outperforms EBR. This implies that nodes with limited storage will have a lower detection accuracy and higher false positive ratio when compared to nodes with lower ERW. V. Conclusion. The opinion logic is a core dimension of trust which reflects the confidence in the adequacy of a node's previous interactions. Malicious activities from compromised nodes can lead to uncertainty in the forwarding behavior of nodes, thereby degrading the network. Thus, it is necessary to design and implement appropriate packet forwarding strategies to address this misbehavior in DTNs. In this paper, we present a mobility-aware trust management scheme based on subjective logic to compute trust between two nodes for data forwarding in DTNs where malicious nodes attempt to degrade the network performance by malicious behavior. We exploit the mobility properties of the PDM to improve cooperation and reduce uncertainty. The proposed scheme outperforms other routing protocols by providing a higher delivery ratio while reducing overhead ratio and delivery delay. Our results also confirm that binomial Dirichlet distribution can be exploited to improve node cooperation in resource-constrained networks.